All right. So in the last recording, we started going over open tubular wall-coated columns, also known as capillary or thin layer columns. Okay. In this video, I want to start out by going over some of the other column types. Okay. So the second major column type in GC is the porous layer open tubular column. Okay. Um, These are very similar to the open tubular wall-coated columns, only typically the walls of the actual column itself are a little bit thicker, as is the coating. Okay, um, and in this case, instead of it being a thin film like an oil or some other kind of uh, polymer resin, which is more common for open tubular wall-coated columns, these are typically thin layer of a solid stationary phase, okay, uh, on the column wall. And again, what distinguishes it from the first type is this is, not a polymeric resin. It is not an oil. It is not, um, you know, a polymer of some kind. It's just stationary phase that is cast onto it, and it's a thinnish layer. Okay, it's not nearly as thin as the open tubular wall coated columns. Okay, where the maximum thickness for those is about 5 microns. This is beyond 5 microns. Okay, so you can think of them as a little bit thicker. All right. The third major column type is the one that you're probably familiar with from organic, and that is the packed column. Okay, the packed column. All right, so here we have our physical column, and it is filled. It is filled with stationary phase particles. Okay, now this column is used for large quantity separations. This is high mass separating kind of stuff, like what you would see in an organic lab a lot, for prep work. Okay, so these are mostly preparatory columns. Okay, they're not considered analytical scale columns. Types 1 and 2, analytical scale. They can only accept a small amount of analyte, but they in generally perform better in terms of separation than a packed column does. Okay, but packed columns have the advantage in that you can prepare a lot of material. Okay, you can put whole grams of material onto certain packed columns and actually get those purified out, which is very useful if you're trying to separate materials that can be separated in the gas phase. Okay. Packed column stationary phases can be things like carbo wax on fire brick, okay, which is essentially crushed brick material that is thermally stable. It's not going to melt or catch fire, coated in a very heavy long chain alkane wax. Okay. Um, that kind of filling or that kind of packing material is not acceptable for porous layer open tubular columns or the open walled or open tubular wall coated columns. It's just not appropriate. They don't separate as efficiently because of that. Okay, and in fact, the packed column exacerbates the path length uh, uh, variable, that A variable, on uh, the Van Deemter equation, where the open tubular and to a lesser extent the porous layer reduce it. Okay? Whenever you're choosing your stationary phase, you choose the stationary phase, okay, to match, okay, properties of the analytes. All right. Remember, back to Gen Chem, like dissolves like. So if you're separating polar compounds, you want a somewhat polar stationary phase. And the more polar the stationary phase is, the more that a more polar compound will interact with that stationary phase, right? And so it will be retained longer. Whereas if you have a very non-polar stationary phase, the more polar compounds are going to get flushed out of the column faster. They're going to interact less, okay? So we choose our stationary phases to match our analyte properties, okay? Um, typically, we monitor column performance um, by analysis of a standard. Okay, and this can be an actual commercially purchased standard, or this could be something that you make in house. You could take, a particular sample, maybe it's one of the analytes that you run during the day. And the first thing you do every morning is you inject a known concentration of this standard onto your system and you analyze it. It is the same injection every day because that will tell you if there has been a change in your instrument. If the column is starting to degrade, you'll see that. If the detector is starting to fall apart, you'll see that. If the injector is damaged, you'll see that, okay? Because in theory, uh, we know that if we inject the same concentration of the same analyte every day to the same instrument, we should get within a certain margin of error, within a certain percentage, right? Statistically speaking, we should get the same response for all our key metrics. Things like retention time, peak width, peak asymmetry, all that stuff should be remaining the same. If it's not, we know there's an issue with the instrumentation. Okay? Typically, we look at things like the retention factor. We look at the number of theoretical plates that are being generated by the column, right? We look at the peak asymmetry, right? We'll look at, at just overall signal, right? Right? Changes in these indicate that there's an issue, and we have to figure out what that issue is. All right. At high temperature, columns will undergo a process called bleeding. Okay. And this is actually degrading the stationary phase. So what this means is that the stationary phase is actually boiling out. Okay. Or in some other way, thermally degrading. Okay. As you can imagine, this will increase the noise, right? So this gives us a reduced signal to noise ratio. Okay. and and it permanently damages the column. Okay, so it reduces the column lifetime. All right. Now, I want you to get an idea out of your head. You will sometimes read or hear people say that they deliberately bled their column because something stuck to their column. You know better than that, right? Equilibria are dynamic processes, okay? They can be very, very slow, but they don't stop. So it is impossible for something to stick on a column. It doesn't do that, okay? It could be very, 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 very sluggish. And so at higher temperatures, you will force that material out of the column because you're increasing the equilibrium rate. But you are not unsticking something because things cannot stick to a column. All right. So that is one point where sometimes you might deliberately bleed a column, but you don't typically want to have that happen because it does more damage than it gives you in benefits. Okay? If you need that high of a temperature to perform your separation, you are better off getting a column designed to operate at that temperature. All right? Okay. All right. We can reduce the bleeding interference. Okay. We can reduce it. First, by using the thinnest stationary phase that we can. All right. Second, all right, we use the narrowest and the shortest columns possible. Okay. And so now you know why open tubular wall coated columns are more popular than porous layer open tubular columns, because the thinner stationary phase reduces this bleeding artifact that we can see at high temperatures. Okay. The other thing we can do, all right, is we minimize oxygen in the column. Now, if we were at the university and able to physically go inspect the GCMS, I would show you that on the helium intake tank for the GC portion of the instrument, there is a filter that the helium gas passes over. And that contains both a desiccant to remove any water vapor that might be in the helium and a deoxygenation salt. So a salt that will pull oxygen out of that carrier gas, thus making it even more free of interferences, because oxygen is needed to the presence of oxygen will accelerate bleeding by oxidizing the stationary phase. Okay, so if we can get rid of that oxygen, we can reduce the risk of stationary phase oxidation. Okay. The last thing we need to do is we need to make sure our carrier gas is the highest purity available, right? So whenever we're buying helium for our GCMS at the university, we buy the purest helium we can get, medical grade helium, okay? Which is 99.9999 9, I think, percent pure. Okay, so we're talking pure down to 10 parts per million. No, no, 1 part per million. Sorry, did my mental math. Okay, uh, folks that use hydrogen, they like to try and get as pure as possible in terms of hydrogen. And they really need to minimize the oxygen in the column because hot hydrogen gas plus oxygen gas equals boom, right? Because we know the expression 2H2 plus, or sorry, 2H2 plus O2 becomes water in the presence of heat. It's also known as an explosive situation, right? Right? All right. Okay. All right. One final note is that the separation, okay, the separation of stereoisomers, okay, requires a chiral stationary phase. All right. We can't just separate a chiral pair of molecules without having a chiral stationary phase. Okay. All right. In packed columns, okay, in packed columns, uniform particle size, all right, uh, increases efficiency and resolution. Okay. It lowers plate height. Okay. Because it reduces, okay, it reduces that path length variable in the Van Deemter. Okay. Um, however, however, it requires increased pressure. Okay. So we can make very, very fine particles that are very uniform in size. And that reduces that A factor of the Van Deemter equation, that various path lengths factor, right? The trade-off is that we increase the system pressure, which means our instrumentation has to be capable of handling that level of back pressure. Okay. Speaking from experience in liquid chromatography, which uses essentially packed columns, right? These pressures can be in excess of 1,000 psi. Okay. Um, and they just go up from there. The finer you make this particle size, the lower the smaller the size of the resulting pores are. Okay. And the higher the back pressure gets. Okay. Now, in gas chromatography, there's a little bit of fudgeability factor there because gases are compressible. So there's a little bit of a compressibility factor, right? In liquid chromatography, that compressibility factor isn't a thing because liquids are not compressible. Just bear that in mind. Okay. All right. So back to talking about gas chromatography. Right? So analyte retention in GC is a function of the enthalpy of vaporization, okay, and the enthalpy of mixing, all right, for the pure analyte in pure stationary phase, okay? And we're treating our stationary phase as a liquid for this, okay? So if we go back to how these separations happen, right, what we have is we have the analyte as a gas, right? It's in the vapor phase, equilibrating with the analyte dissolved in the stationary phase, okay? That's our partition system, right? So here we have our enthalpy of vaporization. Here we have our enthalpy of mixing, okay? And we can manipulate this equilibrium, right? Because we can understand that it is an equilibrium, all right? And so it would have an equilibrium constant, which is equal to K, right? So the natural log of K, all right, is going to be the enthalpy of vaporization divided by RT plus the enthalpy of mixing over RT, okay, plus some constant, all right, okay. And in non-bonding, in non-hydrogen bonding solutes, okay, because hydrogen bonding throws this off, the enthalpy of vaporization when it isn't known can be estimated as about 88 joules per mole per Kelvin times the boiling point, again in Kelvin, okay? All right. So that allows us to adjust this. And it also, you'll notice, it makes the separation a function of the temperature, right? The temperature. That's important, okay? Because there's two ways to run a GC. We can run it isothermally, right? And if we're doing an isothermal separation, then we hold T at a constant, or we can do it with a gradient, okay? So we change the temperature over time, okay? Isothermal runs are preferred. Gradient runs are often used when isothermal runs fail, okay? Gradient profiles are described, right, by looking at the temperature as a function of time, okay? The most simple gradient, pattern is the simple linear increase over time, okay? Where, here's our initial temperature, we inject, and then we increase the temperature over time, right? But there can be all kinds of different patterns. You might hold for a little bit, gradient increase to another temperature that you hold at, decrease a little bit, hold there, increase a lot a bit, hold there for a long time, and then increase to the column maximum or something like that. They can get very complicated. They don't have to be very simple patterns. All right. In the next video, we'll pick up talking about things like carrier gas, and we will talk about the various GC detectors and the different injectors before we move on to liquid chromatography. I'll see you then.